mentioned, means like we are going to mostly talk about the metal oxide and graphene, and then nanocomposites, how they are useful or how they could be useful for functional applications. So we'll start with the outline of the presentation. If I mention that we'll first introduce actually why, what is the motivation for actually, you can say, this metal oxides and the graphene. And then we'll start with the actually first iron oxides, then iron oxide. We'll understand some very basic actually research, what we have tried to understand, where the growth mechanism of hematite nanoparticles, where we will emphasize or we will showcase the role of maghemite as an intermediate phase there. So, which has been almost more than 6 decades of kind of mystery, it's like how these hematite nanoparticles that grow. And it's not that much easily possible to synthesize hematite nanoparticles of smaller sizes. So, and then we will discuss about the graphene, where we have actually come up with a novel approach, synthesis using the waste battery electrodes. So, where we'll be again highlighting the introduction part, what is the requirement of we have actually synthesized graphene from discharged dry cell battery electrodes. And then moving forward,
Ajit sir, you're not audible. Hello?
actually results where we have used this graphene.
Ajit sir, you're not audible.
Dear participant, there is a small technical problem at the speaker ends. He'll be joining in back soon. Please bear with us. Thank you. There is a small technical issue at the speaker end. He'll be rejoining in soon. Thank you.
Yes, Darshan sir. Unmute and tell me, sir. Hello.
Yeah, I have rejoined, sir. I have rejoined. Now it is fine. Yeah, I'll share. Okay, sir. I didn't realize. Sorry, sir. Sorry, sir. Yeah. Sorry, sir. Yeah. Uh. Yeah. Okay, fine. I'll start. Don't worry. I'll start. Now, can you see me, sir?
It's sharing.
Okay.
Still yet to share your PPT.
Yeah. Maybe some net connections are actually. I think that might have created problem. I feel.
Yeah.
So no problem, sir. We still have time. We can manage. No issue.
Speaker has joined.
Okay.
WhatsApp alone. Your screen. You should start sharing.
Yeah, I'm trying, sir. I'm trying. Just can you see me, sir? No?
Yeah, now it's there. Yeah.
Now it's there, sir?
Yeah, you already gone to 11th slide. So,
Now it is fine, sir?
Yeah.
Okay, fine. So everybody can hear me, sir?
Yeah, from the first slide you can continue.
Okay, so from first slide, sir, I'll start again. No issue, sir. Okay, fine.
Dear participants, there was a little bit technical slag. Okay, we are starting again. Please bear with us. Yeah,
okay,
you can start.
Okay, first, I'm sorry for all the inconvenience. Okay, so
okay.
Fine. Okay, so we'll start again. So this is actually I'm presenting the work of my two students.
All these things have been told. Actually, you can start from second slide.
Fine. Okay, fine. So this is actually first outline of the presentation. We'll go with the introduction and then why actually we are what we are talking about actually iron oxides, and then we'll be discussing about the graphene, which we will be showing actually how we are producing using the waste battery electrodes, and then finally we'll be showcasing actually some of the functional application what we have tried for metal oxide and graphene and composites, and finally we'll making the conclusions and future outlooks. Fine. So the point is actually here just to say that for the motivation why metal oxides actually interesting material what we are trying to explore. In particular, the transition metal oxides, they are interesting actually class of material because as they have the outer d electrons and tolerant vacancies or non-stoichiometry and variable cation valency. Okay. At the same 2 decades, if I say almost last 2 decades, it has merged as kind of very interesting material for various application and owing to its tremendous properties. So right side, if you see, it's like there are promised applications what these two materials has shown actually over the periods. Fine. So in what is important for efficient design of material for desired or targeted applications. So if you see, so the phase
Ajit ji, again you're out. Yeah, Darshan, you can talk. There is a problem from other side only. We are having no problem. He's checking. Just a minute. He's checking. Please bear. From yesterday, it is creating problem. Yeah. You rejoin, sir, first.
Audible.
Yeah. Now it will be audible, sir. It is fine.
Yeah, now it's audible. Yeah, you can.
Fine. I'll start, sir. I'll start. Just a minute.
I think your network. That's why your video and all is stuck.
Yeah, but sir, I want to present. Presentation. Okay, just a minute, sir. Now I'll do, sir.
Yeah.
Now, sir, it is visible?
Yeah. You can make it full screen.
Fine. I'll make it full screen. It is visible, sir? No?
Yeah, F5 you can press slideshow.
Yeah, I'll do, sir. This is fine?
Yeah, fine. Absolutely fine.
Okay, fine. Thank you. So fine. So I think we are focusing here on graphene and iron oxides. That's what I thought of telling you. So this is iron oxides. So I'll be discussing. So what is special about iron oxides? So iron oxides we have actually in 16 forms, particularly the oxyhydroxides and the oxides, if you see. So here the most important ones, if I say the wurtzite, magnetite, hematite, and margamite, which has been explored for various applications. Fine. Here the involvement of initial formation of oxyhydroxides, people have shown that inevitable in the synthesis of iron oxides. So understanding their formation pathways actually plays a crucial role in to achieve the required phase and morphology of iron oxides. Fine. So here if you see that what we are going to discuss here, how the hematite nanoparticles, they grow, okay, the mechanism about, and we will be highlighting the role of margamite as an intermediate phase in a particular synthesis approach, but we will be discussing that chemical actually co-precipitation. Fine. And so here, if I talk about the hematite, actually, you all are aware that it is abundant, stable, and non-toxic and super paramagnetic, actually paramagnetic iron oxide used for various biomedical, environmental, and functional applications. So understanding the interrelations between the formation pathways and the growth behavior is definitely vital for the rational design of shape and size controlled hematite nanoparticles, what people have shown. So this is the synthesis protocol, what we have actually followed, where we use the chemical co-precipitation followed by thermal treatment. Okay, so this is the synthesis protocol. So I'll not actually go in detail, but here now we actually talk about the characterization, where what we have observed actually after the synthesis. What we have observed, if you see the X-ray diffraction actually pattern, it's perfectly matching with the hematite phase. So phase is confirmed. Second point, if you see the SEM, scanning electron microscope micrographs, scanning electron microscopy, actually micrographs, if you see, we have a larger sizes, but with a large distribution. Okay, so if you see the average particle size right hand side, if you see what we have mentioned from SEM, if you get, that is a 207 plus minus 162 nanometers. So size is large, but at the same time distribution is also actually on large side. And XRD profile, if you see, we calculate the crystallite size, that is coming almost, you can say, 250 nanometer. So they are very close, but definitely means like there is a difference, and this is the difference what we are getting due to the different techniques involved in getting the sizes, actually, you can say, or the distribution. Then we confirm the same from transmission electron microscopy. If you see, we got the actually variation. If you see the C image, if you here, and then we went actually even for the high resolution lattice fringes, where you can see the like confirmation of the phase with the interplanar despacing. Okay. So the first question, what it comes here, how the hematite phase evolves. What could be the reason behind such abnormal growth, what we have observed here. And then the first thing what we can start with, to know about what is the initial or the precursor phase which forms during the synthesis. Okay, fine. So that is how actually we are going to start with. So initial precipitate, when we try to actually investigate, we found out that the initial precipitate is lepidocrosite, okay, that gamma FeOOH with average crystallite size of 26 plus minus 1 nanometer. And then even we just actually heated up to 150 degrees centigrade before going for actually, you can say, the further heat treatment. then we found out that there could be an actually intermediate phase, what we call as maghemite, with the crystallite size of 4 nanometers. So if you see the right side, actually below, if you see, we have shown the AICTE graph, okay, AICTE patterns, where it shows the lepidocrosite and maghemite phases, actually. And then if you see the right side, how the reaction, or the, you can say, reaction path might go forward. If you see that 2 actually gamma FeOH, that is lepidocrosite, when you heat up to 150 to 350 degrees centigrade, it actually transforms to the gamma Fe2O3, that is nothing but the maghemite. And then this maghemite, further, if you go, actually, you can say more than the 350 degrees centigrade, it transforms to the hematite. So the formation pathways goes with actually lepidocrosite transforms to maghemite and then hematite, okay? But if you see in terms of sizes, lepidocrosite, what you start with, that is a 23 nanometer, and then 4 nanometer, what is the size of average size for maghemite, and then hematite, suddenly you get the 252 nanometers. So if you see, there is a huge difference, actually, you can say what you start with, what you have actually for the intermediate phase, and then what you have actually for the hematite or the product or the final phase. The point is here, one thing we have actually made clear, that the size is increasing, actually, you can say enormously at this actually stage where the maghemite is transforming to hematite, where the size is increasing from 4 nanometer to 250 nanometer. Fine. So now we will try to unfold the growth mechanism, okay? So what sometimes people actually earlier they have told actually about the chain mechanism, where they say that 50 to 100 neighboring maghemite particles which aggregate and form hematite particles, okay? But this aspect is always debatable, because actually you can say people haven't elaborated much on this mechanism, how actually you can say such things happen. Now, our immediate goal is to propose a growth mechanism for such abnormal actually growth. That is what our concern is. But for that, first thing what we should talk about, that maghemite growing first and then transforming, or maghemite is transforming first and then growing. So if we have to clarify on this aspect. So if we see that maghemite is having the lower surface energy and it is actually metastable as well, okay? But at the same time, so that is why it could not be possible. Why? Because if you see the hematite surface energy is on higher side, okay? So hematite is not going to be stable at such a very, very fine sizes, okay? Because of the higher surface energy, okay? So that is why actually what we can, with this argument, we can say that maghemite transforming first and then growing, okay? So now it means that hematite seed formation that happens, and then finally, actually you can say transformation proceeds, and further then growth happens, okay? And this maghemite, actually you can say, if you say maghemite and hematite, if you see maghemite, this is having a spinel structure, okay? FD3M actually space group, and this is how the actually oxygen, and it is having the oxygen ion sublattice actually of FCC actually structure, okay? And that is how the whole formula, if you see actually we can write for the maghemite. But if you come to the right side where hematite, this is the corundum structure you have, and R-3C space group you have, where oxygen sublattice actually is a distorted HCP, where the 2/3 of the octahedral sites are occupied by Fe3+. And this hematite actually conformation, we again did using the, actually you can say XPS, actually X-ray photo electron spectroscopy, and then EPR, okay, electron paramagnetic resonance, okay? So we confirm the same, fine. So phases are confirmed, pathways is confirmed. Now we'll try to understand how the transformation is happening, okay? So now this maghemite, if you see, maghemite actually comes with the 3 actually possible space groups. One is cubic, okay, and another one is tetragonal, based on the vacancy, actually level of vacancy ordering. So if you see the right side, if you come, that's what the oxygen, for the easy, actually you can say follow up, we have only discussed actually the oxygen ion sublattice, how it is transforming from FCC to actually HCP. So if you see, we have actually made it clear actually here how 2 FCC unit cells, they combine and finally actually form the tetragonal of maghemite, and this tetragonal maghemite actually finally with the level of, because if full complete vacancy ordering, then it will transform to actually tetragonal margamite. So here tetragonal margamite which forms, and further this with slight actually dislocation, or you can say distortion, okay, we finally get the primitive cell of a CP. That is the E image actually it has been shown. And if once the seed forms, then how the actually whole actually you can say transformation proceeds. If you see it, it has been shown as a schematic in the subfigure F. Okay, so we have now actually you can say the pathways, how the means like how the transformation that happens from margamite to hematite. Okay, so that is what actually you can say, as I mentioned, that full site ordering actually it leads to C by A, which is actually you can say 3 here for the tetragonal, and then from tetragonal it finally transforms to the hematite. So with that understanding, now we can propose a growth mechanism where for this hematite nanoparticles, where you can have 2 types of growths possible. If oriented attachment, actually you can say it's going to be a combination of the growth mechanism. So with the depending on the actually you can say location specific possibilities. So oriented attachment, you can have actually 2 possibilities when you have FCC and the HCP. Okay, suppose HCP basal plane and then FCC 111. They can come together, and finally, if you see, you can actually have the larger particles of hematite. And if you have the 2 hematite particles, that basal planes, they can come together, and that is how you can form actually bigger hematite particles. But at the same time, post-void ripening you can have where larger particles actually eat away the smaller particles, and that is how become bigger. Fine. So this, just to summarize, the abnormal growth of hematite nanoparticles occurs simultaneously during the margamite to hematite transformation. And this role of margamite as an intermediate phase actually on the growth behavior of hematite nanoparticles we have actually understood here. And then furthermore, the high-end actually in situ experiments definitely can throw some exciting insights what we have discussed here. The work actually was published in Crystal Growth and Design in starting of this year. And this work actually was again actually chosen recently for the 2021 Emerging Investigator actually virtual issue. And then moving forward, actually graphene part, where we try to synthesize graphene from waste batteries. Okay, so graphene, if you see, this is the 1 atomic layer thickness 2D material. Composed of sp2 hybridized carbon atoms configured in hexagonal honeycomb lattice. So you are aware of it, has excellent actually physical properties like electron mobility very, very high, okay, higher thermal conductivity, and then larger available surface area and exceptional Young's modulus, particularly you can say that in the direction of van der Waals bonds. Okay, so it is a layered structure, of course. But the point is actually it has promised actually so much in terms of applications. But if you see there, definitely we have to look for the synthesis approaches. So synthesis approaches till now, if you see, there could be 2 actually category of synthesis approaches. One is top down and another one is bottom up. So top down, if you see that mechanical exfoliation, then chemical exfoliation, and then electrochemical exfoliation. So these are the actually typically 3 categories of top down approaches. And if you go for, if you talk about the bottom up approaches, PVD, CVD, and so on, actually you can have. Okay, but all actually here, if you see that what starting material you are using. Okay, so the point is natural synthetic graphite in the form of powder or rods actually being used for the synthesis of graphene in all actually these top down and bottom up approaches. Okay, fine. So the point is actually, if you see, therefore we have to look at the sustainable way of graphene synthesis actually, and whether it is feasible or not. Okay, so we have actually tried to synthesize the graphene from waste battery electrodes, what we actually see all around actually in our day-to-day actually life. Okay, so the recycling of waste carbon dry cell batteries, it has been focused till now only on recovery of metals like iron, manganese, zinc, and magnesium. However, the carbon rod placed at the center of the battery normally people they neglect, or you can say just incinerate actually. So what we have actually thought of in view of environment safety is the waste graphite actually, you can say, rather can be reutilized. That's what actually our approach actually went to. So that is what actually this is the we tried this work, graphene from discharged dry cell battery electrodes, and it was published in last year in Journal of Hazardous Materials. So we'll be discussing about the motivation, as I said, that utilization of waste dry cell battery electrodes for graphene synthesis. It serves two purposes. First thing, the waste management, and the second point, it decrease in amount of energy and resources spending for production of graphite utilizing for graphene synthesis. Fine. And we use actually electrochemical exfoliation method, where these two graphite rods, what we get out of these batteries, we use as anode and cathode, and electrolyte what we use here as sulfuric acid, 0.35 molar, and then voltage bias, what we use, that 2 volt for 2 minutes and 10 volt for 2 hours. And finally, you can say the product obtained, actually what we get is graphene oxide with the yield of 88%. So that is something interesting. So, and then further we go with the reduction treatment. So we go for heat treatment at 650 degrees centigrade for 3 hours in argon atmosphere. Okay, and finally we get actually reduced graphene oxide, and what we call as graphene actually in most you can say popular way. Fine. So exfoliation mechanism, if you see, means like that is how, means like you can say these ions, if you see that OH minus sulfate ions and then HS4 minus, and then all these actually they go inside the layers. Okay, and that is how finally you can say this they get actually exfoliation that happens finally. Okay, so it has been shown schematically how actually it all happens. Okay. So finally, if you see the characterization part, if you see, means like this is the X-ray diffraction graph and the Raman spectra. Okay, and here one interesting point is, if you see most of the time what people they show an X-ray diffraction graph of graphene, actually normally you see at the very low angle, okay, 2 theta angle, you see the highest angle P. Okay, but here we are not getting. So we actually showed a very interesting analysis in terms of oxygen, actually you can say involved there. So there is a particular level of oxygen actually involved there, which makes actually you can say if you have more than a particular actually level, then only then you will not see actually such that low angle actually peak for the graphene. Okay, so that is what the case actually in our case we had actually higher level of oxygen, okay, involved there in graphene oxide, and even for graphene further. So that is why we were not able to see the lower angle peak. So there is a very interesting analysis. So if you want, you can just have a look at the paper, what the analysis we have discussed there. And then so this was actually why where from it was confirmed. It was confirmed from the TGA analysis. And then we also did surface area analysis using the BET. And it was more or less actually fine. What we got that if you see the RGO, that 27 meters square per gram the surface area. And if you see the morphology, means like that field emission is scanning electron micrographs. So you see that very thin, actually you can say graphene, you can say that is visible actually here, that layers. So we have done actually even the transmission electron microscopy are the same. And if you see such a transparent, actually thin layers of graphene that can be visible. So it is, of course, multi-layer graphene. So that's what actually we got. Fine. So this, to summarize, actually, this like graphene was synthesized from the waste dry cell battery electrodes. And this idea, of course, can be extended for the large-scale synthesis of graphene. So the work has been published in Journal of Hazardous Materials, and later, actually, recently, it has been actually, you can say, patented as well. So, and then now, Miss, like we'll show where we have utilized actually this graphene to further, actually, you can say, to make a nanocomposites of metal oxides and graphene, and further try to show that application part. Okay, so this is what we use this graphene, what we synthesize to make the nanocomposites with the titanium oxide. So if you see, this is the Here, what we try to understand, what we try to do, to utilize the graphene, what we synthesize from waste batteries for the carbon monoxide gas sensing. Okay, so here poor electron mobility of titanium oxide and the less adsorption characteristic of graphene, it can be overcome, what we thought actually, by combining them. Okay, so synthesis part, if you see, is like we actually in situ, this is the in situ synthesis. We followed the hydrothermal actually synthesis route. If you see the schematic, it is very clear where we titanium actually ions, they react with the graphene oxide, and that is how finally you get TiO2 plus graphene, and this TiO2 plus actually it reacts with S2O, and that is how finally you get the titanium oxide plus 2H plus. Fine. And finally, this is what the powder TiO2 RGO nanocomposite powder, what you get. So finally, means like if you see the phase part, we have confirmed this TiO2 actually phase formation. Okay, and then SEM micrograph, if you see, we still see that, okay, fine, it's like graphene is there as a part of the structure. So that is how material. So that is how we made the actually nanocomposites of titanium oxide and graphene. So if you see this like figure sub-figure D, if you see, we have shown the actually you can say carbon monoxide, actually you can say exposure, how the resistance of the material actually that varies. Okay, so this is for 100 ppm if you see, and this right side one is for 200 ppm. Okay, so if you see the sensitivity, how people they measure that delta R over RA, if you see, so delta R over RA for 100 ppm what we got at 0.1, and then for 200 ppm actually we got 0.16. Okay, so that is how actually the sensitivity we tested, and the mechanism actually we proposed that adsorption of oxygen and oxygen ions first, and then this actually oxygen ions they actually interact with the carbon monoxide. Okay, and then finally they form the actually CO2. Okay, fine. So that is how actually you can say you get the variation in the actually resistance of the nanocomposite powder what we have. So if we see, it's like where we stand in terms of properties. So if you see, it's like this is the literature where people they have used gold functionalized ZNO nanowire, okay, and then platinum doped zinc oxide, cuprous oxide composite material, and then gold SNO2 core cell nanoparticles. Okay, so suppose if you see, if you can compare, because there are two types of actually you can say sensitivity measurements. One is delta R over RA, and another one is RA divided by R gas. So if you compare actually here, gold functionalized ZNO nanowire, and then in our case actually 0.05, that's what they got, and here we are showing actually 0.1. Okay, so at the same time 200 actually another actually case, if you see that another parameter, so here 1.12, that nickel oxide nanostructure, that's what actually it has been. So here we got almost 1.12 the same. Okay, so definitely we are competitive in terms of actually carbon monoxide sensitivity, okay, efficiency of the material. Fine. So this work actually you can say, just to summarize, if I say in situ we prepared the TiO2 graphene nanocomposites, and then we tested for the carbon dioxide, carbon monoxide actually you can say gas sensing, and at the same time definitely this material can be tested for other analytes for the sensing actually applications. So this work was published in Bulletin of Material Science almost 2018. And then coming to the where we made the magnetite graphene nanocomposites for biomedical applications. So this was again chemical co-precipitation. If you see the schematic at the left most side, okay, where that is how actually, because the easier the method is, so we use this method actually to synthesize magnetite actually nanoparticles. So here this crystallite size what we got almost you can say 5 nanometers using the line profile analysis of that siding. The average size of the particle which was observed actually from the TEM, that was almost 6 nanometers. So it was, if you see the XRD analysis and the TEM, almost actually they are matching. and super paramagnetic behavior of the particles. If you see that right bottom, actually, yeah, you can see from the hysteresis loop, okay, where we got almost closed loop. So that shows the super paramagnetic behavior of the magnetite nanoparticles. So this is the this is the elemental mapping actually for the magnetite nanoparticles, and actually you can see dark field imaging where you can see the individual particles, okay. But at the same time, if you see, definitely they are in agglomerated form, and this is due to the very nature of magnetic behavior, okay. So normally they get actually self-assembled, okay. So that is very, very much visible here. But if you see the sizes and all, definitely means like it's very, very small, okay. So we have done very detailed, actually you can say, TM analysis for the same. So then further we went to make the magnetite and graphene nanocomposites. So if you see the here you can see the SEM micrographs where you can see the particles at the same time graphene, okay. And right side, if you see, come to the Raman spectroscopic data, if you see that after, actually you can say graphene, actually you can say together that you can say the behavior, or you can say the layered structure, that is not going to be, actually you can say changed. That is the first thing. Second thing, actually super paramagnetic behavior of the particles was actually, again you can say, retained, okay. If you see the right bottom most actually figure, okay, where hysteresis loop has been shown, okay. So it means we nanocomposites realized with, actually you can say without any change in the individual components, okay, in terms of properties and the physical appearance. Fine. And then we went for the antioxidant property evaluation, okay. So here we three types of material. One is actually you can say without any functionalization. It's like one is chitosan coated iron magnetite nanoparticles, and another one is actually where we made the graphene actually and magnetite nanoparticle composites. And then we actually, if you see this antioxidant property evaluation, where we showed that this functionalization actually that definitely that improves the antioxidant property of the bare actually magnetite nanoparticles, okay. And we compared, actually ascorbic acid was used as a reference, okay, to compare the results. Fine, okay. And then further, actually these nanocomposites were tested for the cytotoxicity against various cell lines, okay. So here again we showed that these functionalized nanoparticles, they are actually, you can say, they have the improved, actually you can say, this cytotoxicity cytotoxic behavior compared to the bare one, okay. And these two works, actually we have, one was published in Journal of Material Science, Materials in Medicine, that antioxidant one, and the second one that where we tested for antibacterial and the cytotoxic behavior, it was published in Journal of Materials Research, okay. And then another, actually you can say, the one what I can show you that in terms of application, where iron oxide and the graphene actually we use for the volatile organic compounds which are hazardous actually for the environment to change in some, actually you can say, not actually hazardous kind of product, okay. So here we use this you see that tolu into CO2 conversion, okay. So we showed that if we use this hematite and graphene actually, then we can, actually you can say, change that toluene actually completely to CO2 even at almost, you can say, 350 degrees centigrade temperature, okay. So this is the right side, if you see, it's like this is the hematite and graphene actually with nanocomposite X-ray diffraction, where it shows all the intact, actually you can say, hematite phase structure, and then the morphology where you can see the particles at the same time graphene, okay. So in the SEM micrograph. Fine. So with this, actually we can conclude that we interviewing methodology for the synthesis of metal oxide graphene nanostructures and their nanocomposites actually with graphene actually are demonstrated actually here. Their formation mechanisms were investigated, growth mechanisms were proposed, phase transformations were studied. Okay, at the same time, we tried to show the functional properties of these nanocomposite materials. In terms of actually, you can say outlook, that what oxide nanostructures we have got actually can be tested for various other functional applications, and we can understand and design the other iron oxide nanoparticles with the support of the studies what we discussed actually in the present work, and look forward for various actually applications. So at the same time, it is we want to comment here that it is high time to consider waste battery management as a serious concern. Okay, and the graphene extraction from waste batteries must be practiced at large scale and using further for various applications. So thank you very much for your attention. I'll be happy to take any questions.
Participants, if you have any queries, you can please ask. It was really, Ajit sir, it was a very beautiful talk. Right, you have focused on both environmental aspect as well as other aspects of nanomaterials. So yesterday, I think probably I would have called you yesterday because yesterday was World Energy Day. Right,
okay.
I think you would have been the best person to focus on that because you're speaking of graphene for battery waste management of batteries is a very serious concern. We are thinking of electrifying all the cars, but nobody has thought about what will be the implications of waste generated through the batteries.
Yes, sir. Yes, sir.
Yeah, that is a very, by I think probably 2030 or 2040, that will become a very serious issue. Will be, as we are suffering from solid waste disposal, will be suffering from battery disposal.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes,
so
sir.
Actually, it's a very serious issue of concern. Very nice, very nice. You have taken a very good work of reusing graphene. Yes, yeah, sir. If any queries are there, please, participants. So one of the Karun Kumari has raised a question.
Yes,
what is the synthesis method used for the synthesis of hematite?
This was chemical co-precipitation method.
Yeah, Karuna Kumari, your question is answered. Chemical co-precipitation method.
I can show you. Actually, you can say even the synthesis protocol. Actually, here. Yeah, this one. Actually, if you see, this is the chemical co-precipitation followed by thermal treatment. Okay. Sir?
Yeah.
Hello, sir?
Yeah, I'm there. And one more question is, what is the fraction of TiO2 and RGO in the nanocomposite?
Okay, if you see what actually we tried, it was if I say fraction in terms of volume, if you say, if we tried to, I think 5:1, if I remember correctly. Okay. Actually, that's what means. Like you have to take the, actually you can say starting, you can say chemistry accordingly. But if I remember correctly, I think it was 5:1. That's what the we tried to make. Actually, you can say 5 parts of titanium oxide and then 1 part of RGO. That is how actually we tried to design the, actually you can say starting material. Means like you can say chemistry of the reactants. You can say.
Hello.
Okay.
Hello, good morning, sir. Myself, Vijendra Kupon, sir, from Raichur.
Yes, sir. Yes, sir.
Sir, my question is, thank you, sir, for your nice presentation. Sir, my question is, with respect to nanocomposite, when I seen the some images, there is a agglomeration, cluster formation is there. I think in the 2 phases, when we've gone through some of the some images. So
Yes.
the question is, when we want to improve some of the functional properties, so I think if agglomeration is there, then it is difficult for us to improve to enhance any mechanical, any kind of properties. It may be any physical, mechanical, or
yeah, that's true. That is where actually, if you see, means like you can use some actually you can say capping agent. Okay, so that can definitely improve the, means like you can say in terms of not having the agglomeration. But because suppose we this is magnetite, correct? Magnetite is magnetic in nature, so normally they can actually come together. So self-assembly people have seen, actually you can say, but definitely that is a concern, what you said, no doubt.
And with respect to SEM, when we are going for nanoscale level, I
Mhm.
think, I need to learn, sir. The thing is, can we have to go to with the EBSD also, electronic backscatter diffraction also? I think when you're going for nanoscale level material.
Actually, EBSD, that's what means like what you are, what you want to look for. I think based on that, I think you can think of. But EBSD is mostly people they practice EBSD. Mostly people they practice for orientation of the
It's
particle.
basically for grain orientation. What is
Exactly.
the orientation of the grains within the grain or among the grains they see? Then
Yeah.
okay, suppose you are doing rolling, going for ultra-fine grain structure,
Yes.
can we do, whether it is so important to have orientation problem in this case of nanocomposites? Is there any specific reason here where we need to study the orientation of these particles, Dr. Vijay?
Because powder materials, I don't think actually orientation, knowing the orientation, I think is going to have of any use in terms of application. Because powder normally they will be having the random orientation, correct?
That's what I don't think EBST might be of good help or great help in this
Yes,
kind
sir.
of nanocomposites. What I personally feel.
Yes, sir. Yes, sir. Yes, sir. You are correct, sir. You are correct. So, that's true.
Mr. Kakanur, I think you got your answer. Vijendra Kukanur. Hello. Okay. Any other questions? What if RGO fraction is increased? Is one more question.
What, sir?
Yes, sir. Good morning.
What if RGO fraction is increased?
Okay. In which case, sir? Must like,
Probably
okay,
it
offer
is
all the
TiO2
properties.
and
Okay.
RGO only. The same person has asked, Karuna Kumari.
Actually, if RGO fraction, if you, because here it's all about the kind of to utilize, I mean, to have the synergistic effect of metal oxide and graphene both for the properties. So suppose if for TiO2, if you remember, it's like I can show you what was the motivation for the. So suppose if you see here that this TiO2 actually is having the poor electron mobility, but at the same time, if you see the graphene, actually it has the less absorption characteristics. So to combine both, actually the whole point is to utilize the synergistic effect of both, correct? So if you use more graphene oxide, then you will be actually facing this absorption actually issue, correct? So that is why actually it's always there has to be some optimum, actually you can say, fraction of both oxide and the graphene. Just I'm giving one example of this CO gas sensing, but it can be actually, you can say, utilized, or you can say the message can be utilized for any application. So definitely it's all about why we are going to combine, or you can say nanocomposites or composites, just to utilize the, you can say, the properties of both the, actually you can say, species, correct, or the material. So we have to go accordingly.
Yeah, because a lot of people are working, even if you come to ISC, there is a nano sensor where
Yes.
they are working on these kind of nano sensors basically to detect emissions of prime importance like carbon dioxide, carbon monoxide,
Yes,
NOx,
sir, yes.
hydrocarbons. And
Yes.
it will be of great help if we can synthesize some nano composite which can sense these kind of gases.
Yes, sir.
And the sensitivity, if it is good, then probably accurate measurements can be made.
Yes, sir. Yes.
And that is a need of the hour today to see what is the levels of these gases in the atmosphere,
Yeah,
as
with
well as
all
in the exhaust.
pollutions and all, actually, which is coming actually nowadays.
Yeah. So recently, what has happened is you would have seen a lot of automobiles now are incorporating a built-in gas sensing
Yes, sir. Yes, sir. Yes, sir. That's true.
sensors to see the exhaust levels so that it meet stricter emission norms set by the government agencies.
Yes,
In
sir.
that
Yes,
sense,
sir.
a lot of research has been going on in this. It's very good to see that you have taken up a wonderful topic for your research and you have done good work as well as publications in this area. Nice to see you.
Thank you, sir. Thank you. Thank you. I think credit goes to all students only, sir.
Okay, one more question is, Sir, how that is your graphene oxide with metal oxide makes the conventional sensors to be independent of external heating element and make the sensors to work at room temperature, and also how the sensitivity selectivity will be affected in adding this that is graphene oxide to metal oxide. That's what I was discussing. I think similar to that, the question has been raised by Lakshmi Srinivas A. Could you answer,
Okay.
Professor?
Mm-hmm. So this question as can I see somewhere? I think here.
Yeah, you can see in your chat box.
Chat box, huh? Okay. Okay. Just. Okay. So I'll just stop sharing, and then.
No, along with sharing only you can see. If you come to bottom,
Okay,
you can see the participants. Next to participants, there is a blue color.
Okay.
Message.
Yes.
Just click on that.
Okay, fine. Got it. So how the RGO with metal oxide makes the conventional sensors to be independent of external heating element and make the sensors to work at room temperature? Yes, exactly. Actually, that's what. If you see our what we have done the experiment for sensing, that is at the room temperature, and that is where the point is actually. If you see, because if you go at the higher temperature, automatically actually the sensitivity that goes on higher side. Okay, so the actual challenge is to make the sensors actually more effective at the lower temperature or at the room temperature. That is the best one. Okay, so in that definitely means like you have to have actually some material design aspect where this actually resistance variation can be picked up, actually you can say easily at the lower temperature. And that is where actually you can say we try to have this titanium oxide and RGO combination both, because RGO can have the, actually you can say electron mobility actually faster, correct? And titanium oxide is actually suffers with the poor electron mobility. So that was the whole logic, and that is why we were able to show good property even at the lower temperature. Okay, so that is the crux part. So, but that is very important aspect, surely what you mentioned about.
Okay. One more question. If you have any information about graphene compatibility, can you please share one of the person, Kiran Thakur?
Okay. Graphene compatibility, actually, that's what it depends actually what application you are looking for. But suppose biomedical applications, many people they are talking about, of course, but there are, of course, a lot of other concerns as well. So it's still a lot of research actually going on. So compatibility definitely one aspect. It has to be looked at actually not only for graphene but for many other nanostructured materials and nanoscale materials. Okay, so
one more question: what are the current research trends of using graphene oxide and metal oxide nanocomposites in sensor applications?
Yeah, definitely. I should say, it's like it's in where you can say. You can say many people they are taking up. I think recently, if you want to have a look, the one book chapter we published where we actually you can say very comprehensively actually we have actually brought there actually all the points are what most of the work what people are doing is graphene oxide and then metal oxide nanocomposites for sensing applications. So it was I think last year only it was published, so you can have a look that book chapter. Okay, that was where we focused actually on these nanocomposites, how the people they are using for sensing applications.
Yeah, I think any more questions? If any specific questions are there, you can ask. Otherwise, we'll end the session.
Okay, so just one moment. I'll just tell the
title of the book is
title of the book, of course. I'll just one moment. I'll tell. So that title of the book. Just a minute. So the title of the book is that is actually
you can share with me. I will then put up.
Yeah, actually that is Comprehensive Analytical Chemistry. That is the 91 volume, The book chapter name is Graphene-based Chemiresistive Gas Sensors.
Comprehensive volume.
Comprehensive Analytical Chemistry,
Comprehensive
published by
analytical
Elsevier, volume number 91.
Okay.
And the book chapter name is Graphene-based Chemiresistive Gas Sensors.
Graphene based
Chemiresistive Gas Sensors.
gas sensors.
Page number 149 to 173.
Okay. Okay. I think no more questions. In fact, it was a very good talk. Probably even you can look at iron as a material for battery manufacturing.
Yes,
Because metal, you can see aluminum, metal aluminum has been recently is picking up for making battery
yes,
materials.
sir, yes, sir, yes,
Yeah,
sir,
yes.
yes.
And even IIC, one of the professors has tried with iron as a material for batteries, and he has showed that it has got good power density, energy density. Probably coming years, this might be wonderful research to take up and develop a good battery.
Sure, sir,
Because
sure.
even because in our country we are suffering because we don't have the lithium reserves as such in our
Yes, sir.
country, and
Yes,
in near future we are dependent on battery vehicles, and we need to see alternative materials for
Yes, sir.
making batteries. In that sense, this iron oxides, the
Yes, sir.
graphene material, aluminum for that matter will play a very important role in
Yes,
future research for developing battery technologies. As such.
Yes, sir, yes, sir, yes.
Thank you very much, Dr. Ajit Srivastava, for giving such a wonderful talk.
Thank you very much. Thank you very much, sir.
Thank you once again. Hope to meet you in near future to work, have a collaborative research work with us.
Sure, sir, sure, sir, sure, sir.
Okay.
Thank you very much.
Thank
Sir.
you.
Thank you.
Dear participants, the link for feedback is shared in the chat box. You can share your feedback, and we will join at 11:30. And here to one more eminent person who is a professor in IIT Madras, who will be speaking on magnetic materials. Ajit ji, you have known
Sir,
KG Pradeep,
I'm signing
who
off.
worked under Puno. He will be delivering talk at 11 o'clock.
Yes. Thank you, sir. Thank you. Thank you, sir.
Okay. Thank you, Ajit ji. Thank you.
Have the contact details of
You can visit the VNIT Nagpur website. There you will get
Okay,
his lab number. You can directly contact him. If you want, I will also
Okay,
share his email ID. It's there from his website. Huh?
Okay, sir. Thank you, sir. Thank you.
Thank you, Lakshmi Srinivas. Okay. We'll leave the meeting and we'll start again at 11:30. Please, I expect all of you to join, and that is also a wonderful talk on magnetic materials. Thank you. Yeah, Pradeep, you are there, no? Hello.
Hello.
Can you hear me?
Hi there. Yeah, I can hear you. Yes, yes.
Okay, your voice is also great because from
Yeah.
yesterday evening and today morning, we
Uh-huh.
had some issues with other universities' network.
I see.
Today
Okay.
morning, Professor Ajit Srivatsa,
Right, right. Yeah.
yeah, he was speaking. So,
Okay. But mine
yeah,
looks okay. I have no issue.
yeah, okay. We'll start
Okay, so we'll wait
exactly
few
at
minutes.
11:30,
Okay.
Pradeep. Huh?
Right, right, right. Yeah. So you
I
will
have,
start, right? Then I can take it. Yeah.
yeah, I have a class. Shall I go for class and come back and join you?
At what time?
Now I had at 11:15. I was
Oh, I see.
waiting for
Okay.
you. I will start. My colleagues will start. I will join you after half an
Okay.
hour.
Fine,
Huh?
fine. So I'll be on mute. Once your colleagues start at 11:30, I'll be ready.
Yeah,
Yeah.
yeah. Thank you.
Okay.
Thank
Thank
you.
you.
Hello, sir. Pradeep, sir.
Yeah, yes, sir.
Sir, this is Amit Kumar here, sir.
Yeah, good morning, sir.
Sir, good morning, sir. So, dear participants, we have our eminent speaker here, Dr. KG Pradeep. So that we have a brief introduction about the speaker here. So, Dr. KG Pradeep, sir, he is currently an assistant professor in Department of Metallurgical and Materials Engineering at IIT Madras. And he completed his PhD from Max Planck University and also from RWTH Aachen University, Germany, prior to working in IIT Madras in 2018. So he was a group head for this atomic probe tomography at RWTH Aachen University, Germany. He was also a visiting scientist at uh, so Forschek Zurich for Germany, and also his expertise lies in the field of correlative microscopy and combinatorial alloy design. And Pradeep KG has has published more than 50 peer-reviewed journal publications in the field of physical metallurgy, magnetic materials, atomic scale microscopy, and having H index of 25, and he is currently the coordinator of National Facility for Atom Trope Tomography, that is NFAPT, as well as he's heading the Max Planck Indian Partner Group at IIT Madras. So here's a brief introduction about KG Pradeep, sir. Sir, over to you, sir, for the presentation.
Thank you. Thank you, sir, for the introduction. So, how long should I present, sir? 1 hour?
Sir, it is up to one. It is.
Yeah, fine.
To one. It is.
Okay.
Okay, sir. Okay, sir.
Okay, thank you.
Okay, thank you,
for
sir.
the
Thank
nice introduction, sir, and thank you for inviting me to your faculty development program. So, as he introduced, I'm working at IIT Madras in the Department of Metallurgical and Materials Engineering. So, today I'm going to present about the different correlative microscopic methods that are available in the recent times, by which we can study the nanoscale phase separation in metallic materials. So, this is a new emerging technical methods in microscopy, plus the advancement that we get in new materials design, including processing, which leads to nanoscale phase separation most of the times, is something we need to have a good access to the details so as to understand their materials behavior. So therefore, I'll cover both the topics so that to a large extent it looks in a comprehensive understanding of what is the state-of-the-art latest generation characterization and the latest materials development that's happening. So as you briefly said, my areas of specialization at IIT Madras, we work on two different aspects. One is combinatorial alloy design, the other is correlative microscopy. That means we synthesize our material in multiple forms, be it thin films or in the form of a bulk, where you have 4 different metallic targets positioned on 4 different sputtering units or magnetrons. Then we simultaneously sputter all these 4 elements at the same time. That means you get in one silicon wafer a library of compositions starting from one direction to another direction. And for example, in this case, you see if you have an iron manganese target on the one extreme and aluminum on the other extreme, you can get a uniform variation in composition as you move from the top to bottom. Similarly, if you move from the left to right, then we get uniform gradient in composition in the chromium to cobalt rich region. That means in one material synthesis process at one step, we are able to cover a large scale of composition variation. And depending on the composition variation, we will have a different phase formation and the microstructure, and therefore we will have very different properties. Now, this is one aspect of non-equilibrium phase formation in the form of thin film. And similar combinatorial approach we also do on a bulk scale. That means from the thin film library, we get a wide range of compositions identified and their phase formation studied with little materials expenditure. And the identified composition or the range of composition, we can then carry forward to produce in the bulk form. So this is a picture of the induction melting furnace, where you can get a master alloy of the fixed composition identified from this combinatorial thin film. And we can use this bulk composition and expand it into a composition gradient by having a split mode. That means we have multiple split modes like this, and whatever predefined composition of one element variation you can introduce in this mold and pour this master alloy into it, so that all these molds will have a uniform gradient in composition coming from a single master melt. That means you can get a wide range of compositions based on what we are doing here, and within the limited materials expenditure we'll be able to study all of these compositions at the same time. So when we produce materials of this nature, where there is a strong chemical variation as a function of production, we need adequate techniques to characterize these materials at multiple length scales. That means we do, on the other hand, what is called a correlative microscopy approach, where you get a microstructure like this, for example, in a scanning electron microscope using, for example, a scanning transmission mode, where you can look at the scale bar and realize these are all nanoscale features of mechanical twins that you can see in a microstructure. But right now, looking into this image, it is only dark and white contrast. There is nothing much we can talk about what is the crystallographic orientation of these twins, or what is the identification of the phases present inside. And therefore, we develop techniques where the same region of interest or the same sample we characterize for their phase identification in terms of crystal structure by using a method called transmission Kikuchi diffraction, which I will present in the later part. And using the same technique, we can identify the orientation of the twins across this volume. And finally, from there, whichever region we are interested, we take to the atomic scale. And then this is the three-dimensional view of the same material, but using the chemical composition as the fingerprint and looking into what is called atom probe tomography. So that means atom probe tomography as a tool that gives rise to the finest possible detail of chemical identification. That means even the parts per million of elements present inside can be identified, and all the elements that are distributed in the bulk material can be distinguished for their spatial orientation, because it is a three-dimensional analysis technique, and this enables us in visualizing the atomic distribution in 3 dimensions as well as the chemical concentration measurement at the most accurate method as far as possible. That means from a 3D bulk material, we have now techniques where we can look at their microstructure as well as their chemical distribution in 3 dimensions, so that we are able to interpret whatever materials that we have prepared with their finest atomic scale distribution detail, so that we are able to interpret their properties in a much better way. So this means, as was introduced, I am heading this National Facility for Atom Probe Tomography, which is a consortium-based infrastructure where, as you see here, we have 8 different partners together with the Department of Science and Technology contributing large-scale funding to get this infrastructure available at IIT Madras for anybody across the country to use this particular facility. This means we have a dual beam focus ion beam where we do all these correlative microscopy methods. We have an electron column, we have a FIB column, so that we can prepare samples in whichever way we want, be it electron transparent or in the form of a nanometer scale needle that can go into this state-of-the-art atom probe tomography, where you can look at the individual atomic distribution in any 3-dimensional volume, and you can do the imaging using this transmission electron microscope of those electron transparent samples. That means you see this microstructure in a projected view here, and you prepare the samples based on the location specific details, something like electron backscatter diffraction, giving you the microstructure. From there you select which region you want, and then you can see them into this transmission electron microscope. But if you really want to get this atomic scale distribution or the individual atomic distribution in 3 dimensions, then from this state you can go into this atom probe tomography, and then you will be able to see the individual atomic distribution in a 3-dimensional space. Now this is an example where you can see cluster of certain atoms together, and there are certain atoms which are isolated in its 3-dimensional space. So to understand what is this atom probe tomography, because this is a unique technique where you can look at the individual atomic distribution, we in principle use all this infrastructure under the umbrella of National Facility for Atom Probe Tomography. And as I said before, anybody across the country are accessible to this method, and this microscope can be remotely operated from wherever you are sitting. You can sit at your office and still operate this microscope. And because it is designed in a way to function for every researcher across the country, this is a quite unique facility that we have in the country today. So briefly to introduce what is this tomographic method. That means you can have a three-dimensional object. Like that means you see a box, and inside the box you have a cylinder, then you have a sphere, then you have, let's say, a conical shaped object. If you look at a conventional microscopy method, that means you use electron beam or an optical light or any other source, secondary source as um, imaging system. Then you are going to get a microstructure which is like this, where all the three-dimensional objects are projected in a two-dimensional form. That means the cylindrical object is going to look like a rectangle, spherical object is going to look like a circle, then you have this conical form look like a triangle. So therefore you will not be able to interpret what is the actual shape and actual morphology of that particular object unless we have more details across the cross section. That means this three-dimensional object, if you project like this, you are going to misinterpret this in different morphology, and more so when it is at a nanometer scale. And you start slicing these, let's say you start slicing this particular three-dimensional object into multiple segments, and you do the same imaging. That means slice one can have information only about a part of the sphere and part of this truncated sphere. So you can see this as a semicircle and a full circle. Now, if you have multiple slices from this location until here, then we may be able to say, okay, this is more like a sphere and not a circle. And similarly, you need more such slices being imaged in the projected form to arrive at this assumed three-dimensional object, which was originally a three-dimensional object. But unless we have a technique that enables to slice into multiple segments and enables to image in a projection geometry, the shape of this object, which is the original three-dimensional object, is a random guess. So therefore, there are tomographic techniques that are developed over the years, starting on a coarser scale with the X-ray microscopy, where you can have a large field of view of millimeter and even more, with a resolution in the range of 100 micrometer. But if you want to study nanoscale features in their three-dimensional shape, then these techniques may not be sufficient. Therefore, you have to come down in resolution. And as we come down in resolution, the field of view naturally decreases because we are going into higher and higher magnifications to get the information. And at the same time, we are getting better and better with resolution. Or the more information to the detail we are able to get using this kind of a comparative chart. That means, depending on the size of your nanoscale feature, we can have something like a focus ion beam sectioning, as I showed in the earlier slide, combined with imaging in SEM plus EDS or EBSD. So you will be able to get multiple slices and the projected or diffracted view of the microstructure of those individual slices. If you go down in more resolution, then you reach into electron microscopy, where you can do energy dispersive X-ray spectroscopy for chemical mapping in 3 dimensions. Or at best, you can achieve the atomic resolution using this atom probe tomography with the reasonable field of view of 100 nanometer to a micron. So this is the largest that you can get today. But the advantage is you are able to see individual atoms clearly visualized in a 3-dimensional space. Now, how this technique works is an example that you can see here. Now, you look at this picture. At the first glance, you look at this picture, you may see a shadow of something here. And typically, one can believe that this is going to be a horse and is being attacked by a lion. But in reality, if you really want to know what is this, what is the object that is giving rise to such a shadow, we really need the original image in a 3-dimension. That means the image that you get as a virtual or a reciprocal space may not fully represent what we are intended to see, because the impression gives us an image of an object or image of an animal being attacked by an animal, but in actual reality, this can be completely different. That means we need all this 3-dimensional information to be in a position to relate what you see in a virtual image into what was the reality. That means imaging is an art where we need as many information as possible so as to have the realistic view of what is it that we are able to see in this shadow form of an image. That means when we do the atomic scale analysis, that means when we go with the nanoscale features or composite microstructures, we can lead to this kind of misinterpretation, what you saw in the earlier slide. And therefore, we need to understand why atomic scale analysis is important. That means when you have complex materials, when there are too many elements that are part of the material, or when you have nanoscale features, or when you have phases which are metastable, then you cannot understand them isolated by one technique. Therefore, you need to have a combination of techniques so that all the nanoscale changes that are happening in material as a function of thermomechanical processing or as a function of any other heating, cooling procedures, leads to the phase separation, segregation, etc., can be properly identified, and therefore the nanostructure evolved can be correlated with their mechanical or any other functional property, and therefore we are interested in looking into the atomic scale details using what is called atom probe tomography. Okay, so let me now briefly introduce what is this technique. As you see from this picture, this technique requires a very sharp nanometer scale needle. You can see the sharp needle obtained from a transmission electron microscope, which has a diameter of, let's say, 50 nanometer in diameter over a length of possibly a micron. Now, on this sharp needle of the sample of your choice, we are going to apply positive potential. And when you apply positive potential, the atoms at the apex of the tip are getting strongly polarized. Or, in other words, the polarized atoms can be triggered for field evaporation. That means, in addition to the positive potential to the sample, you apply negative potential to the detector, and you in principle apply either a voltage pulsing or a laser pulsing. That means for each controlled pulsing step where the base potential is active on the sample, the polarized atoms becomes an ion. That means it gives out one electron back to the sample and becomes an ion. And because we have negative potential on the detector side, all the positively charged ions are being attracted towards the detector. That means you get a straightforward line projection from the origin of your of your atom into a projection imaging of an ion, and therefore you will be able to get a magnified view in 3 dimensions of all the atoms that are present in your material. The biggest advantage of this technique is that the position of the tip and the position of the detector are well known. That means the distance between these 2 locations are well known. And we all know that each individual atom in the periodic table has its own atomic mass. That means to cover the same distance between the tip and the detector, each atom is going to take different time. That means every atom, based on its atomic mass, is going to use different time to reach the same distance. And therefore, when you now get the time taken by each atom to reach the detector of a fixed distance, will be in a position to interpret what is the atomic mass of the species that has been traveling over the distance. And therefore, we get what is called a mass spectrum, where you can now independently look at all the isotopes of all the chemical species present in the periodic table with their number of detection as the number of count. That means you can have different counts coming in, and the chemical species are identified based on their atomic mass and in principle giving rise to time of flight. And you know from the detector position where these individual atoms are hitting the detector. That means using this chemical identity here and the atomic positions over which it is hitting the detector, will be able to reconstruct whatever volume that is being lost in this particular state into a 3D volume, where you will be able to now say that my 3D volume had elements which are nanoscale separated in terms of their chemistry. And you can see at each of these layers, different chemical species are present, which was not possible to see in the original microstructure. But now you are atomistically resolved and you are able to see all the individual elements being 3-dimensionally visualized and separated for their chemical distribution. Therefore, this technique is quite powerful, where you can see based on the time of flight, you identify the chemical nature of the material, and based on the ion projection microscopy, that means the projection over a distance enables you to see individual atomic positions, and therefore you will be able to reconstruct them in a 3-dimensional form. So if I now show you the schematic of how this entire microscope works, that you are applying positive potential to a sharp needle and activate the pulsing so that you know the triggering of the pulse, so that you can start the timer to measure the time of flight over which the ion is going to travel this fixed distance. You can therefore get the coordinates of detection in the detector as x and y, time of flight, which is the time taken by each individual atom to reach from the material to the detector as time of flight. So when you measure all this information, that means 3 different numbers that you get are good enough to reconstruct all the lost material out of your sharp needle into a more representative 3-dimensional volume as what you see here. And this particular image, what you see in a 3-dimension, is called the tomographic view of atomic distribution at the atomic scale. Okay, that means this is a quite powerful technique where you can get all the chemical identity precisely identified, and even ppm level elements, impurities, whatever doping agents, everything can be detected, and at the same time their distribution within the material can be visualized in 3 dimensions. So using this technique, we have studied wide range of nanoscale materials. And it is an emerging technique, as I said, with more and more support from other correlative microscopy methods. And therefore, we are today in a much better position to understand the microstructure of nanoscale features in most metallic materials. So with this, I'll now give an example, a couple of examples of how this technique is powerful in understanding the microstructure of materials. So one classical example is an iron-based soft magnet. So as you all know, the soft magnets are indispensable in life. Whatever application that you see, you will always come across this kind of a soft magnet, where these are toroidal wound cores, which are used for electronic surveillance system, transformers. Even your mobile phones will have all of these materials inside. And typically they are used for transformers and choke systems as well as signal detectors. Now, even if you go to a modern day mall, when you enter the shop at the entrance of your mall, you see this tall structures here. A piece of this material is part of these tall structures. A counter piece of the material is part of all the objects present inside. That means when you take an object, the object will already have a small piece of this. And if you pay at the counter, they will remove this particular piece through a button. If they don't remove it, these towers have the same piece but in a magnetized state. And when you bring this piece from the object where it is connected, which is in a non-magnetized state, it's going to interfere with the field between the two towers, and therefore you get the buzzing noise. So therefore, for all these electronic surveillance systems, these kind of materials are commonly and widely used these days. Now, what is this material? So this material is typically an iron-based compound, where you have iron, silicon, boron, niobium, and 1 atomic percentage of copper being intentionally added, because there is a history to this material. That means these materials, either you have to produce in a millimeter size, huge grain size, to have what is called a low coercivity. So coercivity is a characteristic property of any soft magnetic material. That means the lowest coercivity you have, the easier is for the magnetic field to change from magnetized to a demagnetized state without having any hysteresis. That means we need to have a large enough grain size to be having a low coercivity, or on the other extreme, we need to have nanometer grain size or much smaller grain size to have lowest coercivity. The more lower the coercivity, the less loss on the energy it's going to be. That means now you just see here, if you are able to reduce the grain size D within the range of 100 nanometer to possibly 10 nanometer, for each decrease in nanometer, you get a 10⁶ decrease in coercivity. So this is a very attractive region, and therefore the effort by many scientists for the last 2 decades is to make this material in a nanocrystalline form, so that we can have a very, very negligible amount of coercivity. To do this, the 1 atomic percentage copper and all these elements are important. That means we need a fine nanoscale microstructure. And there are different industrial methods available to produce these alloys with fine nanoscale grains. The conventional one is heating it at certain temperature for 1 hour and then cooling it slowly so that you get a fine nanoscale microstructure. The alternative method is you heat it at a very high heating rate, put it at a certain temperature for a shorter time, but that temperature is much higher than that of conventional annealing. And because these materials can be in the form of thin ribbons, as what you see here, this is the thin ribbon metallic material that we can produce, and you cool it very fast so that you are able to retain, or you are able to nucleate only nanoscale grains out of this material. Now this is now has all been standardized into an industrial practice, and these days you can see these kind of materials being produced by rapid annealing in the presence of stress in a continuous ribbon to ribbon or reel to reel type of a systematic process. Now when you do this, what we need to understand is what is the microstructure evolution, so that we can control the grain size to the nanometer range, so that we have a significant reduction in coercivity. So in order to achieve that, we need to use this tool like atomic tomography. The material in the as produced state is going to be amorphous. That means all elements are going to be uniformly and homogeneously distributed. But if you now have them in an optimized annealed condition, then we are going to see 3 different phases. As you notice, there's 1 atomic percent copper, which is usually difficult to even identify using any conventional microscopy or conventional chemical detection methods, can be looked into atom probe in 3 dimensions, and you can see this 1 atomic percent copper has started forming clusters of 3-dimensional objects being randomly distributed in the matrix. Now, if you similarly look at the other elements within this material, they are all preferentially segregated at different locations in a 3D volume, and this all length scale are there. What you see here is all in nanometers. That means at the nanometer scale, there is a lot of chemical heterogeneity that is happening, and all this heterogeneity influences your property in a much bigger way. Now, if you want to understand the evolution of the microstructure in this nanometer scale, then we have to systematically look into the microstructure evolution. Like I said, the as produced sample is in an amorphous state, and you start heating this material at different temperatures. All that is used for application is more or less in this temperature window, where we are interested in retaining only this iron 3 silicon soft magnetic phase and no other phase that we require, because these are hard magnetic compounds which will interfere with this property of the soft magnetic phase. So therefore, the ideal scenario is to have the soft magnetic phase in a nanometer scale retained in large enough volume fraction within this certain temperature window. That means if you now remember this 535-degree annealing, XRD says everything is in a random, or everything is in an amorphous state. You look at the electron microscopy image. This is a transmission electron microscopy image where there is no nanometer scale feature visible, and the diffraction pattern looks everything is amorphous. If you look at the 555 degrees X-ray diffraction, you can see there is a hint of iron 3 silicon formation. If you look at in TM, you see a lot of these nanocrystalline grains that are formed, but the microstructure at high resolution looks a composite microstructure. That means you have some crystalline phase of 7 nanometer being embedded in an amorphous matrix of whatever that is the leftover material, and the diffraction pattern confirms that you have an amorphous matrix because of the halo ring pattern, and you have the spot pattern corresponding to all these nanocrystalline grains that are present inside. So this is what you can understand looking into these microstructure. But we don't know what is this atomic distribution of elements in 3 dimension, and when the system is amorphous, for example at 535, what is the chemical constitution of the material. So when we now want to understand this atomic scale information, then we'll go into the cluster evolution. For example, I'm going to show only for the case of copper, which is 1 atomic percentage. You can see in an atom probe, in an as prepared state, all the copper atoms are homogeneously distributed in a 3-dimensional volume. At 535 degrees, where X-ray diffraction and transmission electron microscope said everything is amorphous, you can see a large volume fraction of clusters of copper that has emerged from a randomly distributed copper matrix. That means all these individual atoms of copper started coming together and form these nanoscale clusters throughout the 3-dimensional volume. Now, as you keep on increasing in temperature, you can see here the size of the copper clusters are increasing and the number density of the copper clusters are decreasing. So this information you can only get from this kind of an atomic scale analysis, and I will show you later what happens if you try to see the same information in a projected microscopy. But in principle, one can notice that as we increase in temperature, the cluster size increases, the number density decreases, and it can easily be quantified by this kind of a graph where you can see with increasing annealing temperature, the number density is decreasing and the cluster diameter or the size is increasing. Now, based on this difference, you can now categorize this evolution to 3 different stages. Stage 1, where you have the emergence of the cluster with the highest number density but the smallest size. And stage 2, we have reasonable volume fraction of clusters but with the coarsened nanoscale features. And stage 3 is the almost negligible number density but very few larger size precipitates that have emerged. Now, if you want to now understand what is their mechanism of growth and what is the crystallographic nature of these clusters that has emerged from a completely amorphous state, then we can further go into the atom probe data, look these atoms in 3 dimensions, and you can see where cluster regions are all identified with this kind of a isoconcentration surface, but individual copper atoms are spread everywhere. Then you can now even zoom in and see there are certain locations where individual copper atoms or individual copper clusters are in contact with each other, and there are locations where they are isolated. Now, if you now zoom in only to this part and see the individual atomic distribution, and you can see here there is large amount of copper atoms forming these kind of clusters, whereas a bigger cluster stays isolated. 2 clusters of similar size, they have started forming a small necking region. Now you can further visualize this in this manner. You can see here the clusters are of similar size necking. Smaller one stays isolated, bigger one stays isolated, and you can even measure the concentration by having a cylinder going through this cluster region with the necking in between and see how the concentration of copper has increased between the 2 different clusters, which gives rise to the phenomenon of what is called coarsening, necking, and coagulation. But if you go to a later stage of annealing, let's say at 695 degrees for 4 seconds, now you can discretize the entire three-dimensional atom group data set using concentration threshold. That means all the iron silicon rich nanocrystals can be identified in the silvery color with the 20% threshold concentration of silicon. The copper clusters can be identified with concentration threshold of 3%, so you can see this one. And the remaining elements of boron niobium are forming part of the rest amorphous matrix. Now, in this composite microstructure, where you have an amorphous phase rich in niobium boron, you have a crystalline phase, nanocrystalline phase rich in iron silicon, then you have a pure copper cluster. It is still coarsening beyond this temperature, and now this coarsening cannot happen by the necking process as what you saw in the earlier slide, rather by what is called the classical Oswald ripening. That means, as you know from a chemistry background, that when two objects of dissimilar sizes are together, the smaller one dissolves, bigger one grows, and therefore you get what is called the coarsening of these clusters by Oswald ripening. Now, all that you are seeing now is a distribution or a microstructure evolution in 3 dimensions. If you try to see the same in a projected view, even by a high resolution electron microscope, you can see there is a nanocrystal here. Do the chemical mapping. At best, you can see the copper cluster distributed in this sporadic form, but not in the 3-dimensional form as what you saw before. Now, even if you try to attempt to see whether these clusters are a crystalline cluster, you can still do in an atom probe, take one isolated copper cluster in a remaining matrix of iron and try to get what is called a spatial distribution map. And in this case, you see there is no correlation as a function of distance. So you can say the cluster of copper atoms have come together to form this kind of a 3D volume, but there is no crystallographic basis for it. You look at the stage 2, a slightly annealed state, take the same single copper cluster, slightly coarsened in size compared to this one. And as you measure the same spatial distribution map, now this time you are able to see a perfect correlation in the intensity of the spatial distribution at neighboring distances, which means the distance between the two maximum intensity peaks is 2 angstrom. Now, if you assume this is going to have a 1-1-1 orientation of an FCC crystal, then you can say the copper cluster is a face-centered cubic copper cluster with a lattice parameter of 3.6 angstrom. That means even in a 5 to 6 nanometer object in a 3-dimensional shape, we are able to get the atomic distribution, precise chemical identification, plus the crystallographic information. A similar crystallographic information can also be obtained what is called a field ion microscope, where you can image individual atoms. That means the same composite nanoscale microstructure in the form of a sharp needle is now imaged in a process screen using an imaging gas that can be a combination of hydrogen, neon, or helium, any mixture. All the individual bright dots you see, the fluorescence that you see in the particle screen, is responsible for one atom being present on the surface of the strip. And now this circular ring pattern you see is called the crystallographic pole, and all these individual dots are individual atoms sitting on a specific crystalline lattice, and therefore you are able to see this specific crystallographic pole. Now, looking at the distribution of the poles, one can identify what is the orientation of the tip or the grain that is responsible for this imaging and the atoms that are occupying. So this is the only method in the world available where you can see even what is called point imperfections or vacancies that are present in the material. The alternate way of looking into the crystallography of nanoscale features is to get what is called field desorption imaging. That means when you do this atom probe tomography, you can look at the detector event hit map and see where we have a variation in intensity of the hits. Now, looking into the intensity of the hits, you can see there is a zone line, and you overlay this detector event histogram on top of a stereographic projection. Then you will be able to zoom in and identify the exact crystallographic poles that are present along this particular desorption image. That means the surface of the tip giving rise to this crystallographic feature can be mapped using a stereographic projection, and their crystallographic planes can be identified. So another example of how this kind of analysis is important for nanoscale materials is the max phase. So in the case of a max phase, it is not a purely metallic material. It's a well-defined stoichiometric compound. That means it needs to have a fixed stoichiometry in terms of the chemistry, where M is an early transition metal, A is an A group element in the periodic table, and X can be carbon or nitrogen. Now, when you achieve a strict periodicity, depending on the value of M, we are able to get a unit cell or a super cell, a nano-laminated unit cell, which is made of a layer made of only A group elements, another layer made of M and X. That means this M and X is strongly bonded, and this is going to behave like a ceramic layer, and the A layer is going to behave like a metallic layer. That means you are going to get a composite property coming from a composite microstructure, which is now can be distinguished from a disordered carbide, where you have random positions of the X element, which is carbon or nitrogen, and the A and M elements into an ordered microstructure where M and X are together and A are isolated. That means the A layer gives rise to metallic conductivity, M and X gives rise to the ceramic behavior. That means a material of this nature is going to have unusual and unique set of properties. That means it can exhibit both metallic as well as a ceramic characteristics, which means it can have electrical conductivity as well as thermal conductivity, and it can also have oxidation resistance. So I'll give you an example of how this oxidation resistance, which can be used as a self-healing component in large-scale structures, has a beneficial property out of this max phase. So this is an example of self-healing. That means when you have an aircraft and this aircraft has, let's say, these turbofan blades inside, which is now made of a high temperature superalloy, let's say. Now all these blades have sharp edges, and when this kind of a blades, or when the aircraft flies in a high altitude, which is at sub-zero temperatures, and suddenly it lands in a desert, which is at 40 to 50 degrees, and when the sand particles on the desert impinge onto the sharp edges, there is a very high probability of introducing local deformation or the cracks on the surface of these sharp blades, which are quite expensive. Now, this is a schematic that represents the difference of what is called self-healing. Now, when you have the material exposed to these extreme environments as well as impact coming from sharp objects, you can induce a crack, and because this fan is rotating all the time, you can have counteracting forces acting on this crack region, leading to a catastrophic failure. Now imagine you have a protective coating, which is, for example, a chromium to aluminum carbide type of a max phase self-healing coating. Now this max phase coating gives you additional hardness required for the crack to not propagate, but even if the crack is formed on the surface of this high temperature material, then the aluminum present here, which is the A element, preferentially reacts with atmospheric oxygen because of the temperature difference and forms a layer of alumina. That means if the A layer element comes out of the max phase, reacts with oxygen and forms this alumina, and this alumina is much more harder than the sand particles that you have, and therefore we are able to get a protective coating formed at the surface of the max phase, thereby preventing the propagation of the crack and therefore enhancing the lifetime of this particular material. Now an example of how this has happened is this one. So we make a thin film coating of the max phase chromium to aluminum carbide, annihilate at 1120 degrees for 4 hours, and see what kind of an oxide that is forming on the surface. That means this image what you see on the top is the same oxide. Because of better contrast, I put it here. You see these nanoscale grains of oxide of aluminum is formed on the surface, and when you add the same max phase with 0.7% of silicon doping, we are now interested to accelerate the formation of oxide formation in situ at this temperature in the atmosphere, so that we can get much thicker layer of this oxide, which is a protective self-healing coating. Now in the presence of a silicon, as we notice, the grains that are formed in the oxide are much more finer. This is the same oxide what I have magnified here. You see the contrast here, the grains are much more finer in the presence of silicon, whereas in the absence of silicon, the grains are much more coarser. That means you get smaller grain size when you start adding silicon to a max phase. A layer thickness improves by 40% compared to what you have in the absence of silicon. That means when you have a crack as deep as this, in the presence of silicon, you're going to fill this crack much more faster than what it can happen in the absence of silicon. That means the concept of self-healing works when these kind of a unique combination materials having ceramic and metallic property works together. At the same time, the process or the kinetics of self-healing can be activated by alloying certain species so that the region or the depth of crack can be healed in a much faster rate. So in this kind of material, now the question is, what is this 0.7% silicon doing and why it is enabling in improving or accelerating the kinetics of the phase formation? So to understand this, we produce these alloys with a range of silicon content. That means, again, we use the combinatorial method as what I said before. So this is a unique combinatorial synthesis method where you have a split target. That means chromium silicon carbon has one target, one half. The other half is chromium aluminum carbon. Now this is the arrangement of the substrate you have over a large substrate area. All these individual square represents one substrate piece. Now when you do this sputtering of these combined or a composite target with half of two different chemistry, you get a range of compositions with varying silicon content from the top to bottom. Now this represents this particular region where you have all of these individual squares represented for their silicon concentration. That means you go to the top of this first substrate, you will have no silicon. As you come down to the middle part, you get maximum of 1.4% of silicon added to this chromium silicon carbide. Now you look at their properties, that means you need all of these samples prepared at the same time, 1120 degrees for 30 minutes. You can see what is the amount of scale, that means the oxide scale that is formed in the atmosphere when you did this annealing treatment for these kind of materials, and the layer thickness is plotted as a function of silicon content. Now as you notice here, this is the oxide that is formed with 0.3% silicon. The more increase in silicon content, you can see the layer thickness is increasing. The more the layer thickness is increasing, you will be able to notice that at 1% silicon, you have the highest layer thickness of oxide scale that is formed, which is responsible for the self-healing behavior. When you increase more than 1% silicon, the layer thickness reduces or layer thickness decreases, and therefore you have the loss in layer thickness or the reduction in self-healing. Now, if you want to understand what is happening between the sample with 1% silicon, where you get the highest layer thickness, and the sample without silicon, now we are interested to know what is the role of silicon and how the silicon influences this oxide formation. Okay, so now these two conditions we'll examine in detail with different microscopy methods. So that means when you look at the X-ray diffraction of a 0% silicon added max phase, and for example a 0.7% silicon added max phase, look this in KM, you can see these columnar microstructures, and the diffraction pattern tells us that this is a single phase material, max phase material in an ordered state, because all these are single phase patterns. And look at the same at 0.7% silicon, you get the same columnar grains, but a slightly reduction in the width of the columnar grains by, let's say, 0.43 of a micrometer is a reduction in size compared to 0.56 when you don't have silicon, whereas the diffraction pattern looks exactly the same. So now what is silicon doing inside? What are these contrasts? We have no idea. So therefore we went into a high resolution imaging, where you now try to image the same material at much higher magnifications in a STEM mode. Now you see that this small region is being magnified into this big region. Now you see the more and more magnification we go, we are able to see some uncharacteristic defects. That means some V-shaped striations that are visible on the microstructure. And when you do the chemical mapping of all these elements, we are able to detect chromium, aluminum, carbon, which is the max phase, and some amount of oxygen inside, but all of these elements are homogeneously distributed. Now the same thing we did with the 0.7% silicon added material. Now we are able to see the same columnar grains. We zoom in this particular region, and then we try to see what is a microstructure in the zoomed in state, and same uncharacteristic V-shaped defects that are visible, which are all consequence of a thin film growth in the nanoscale phase. And then you do the chemical mapping, and suddenly you see the presence of silicon identified in the form of a V-shaped geometry. That means silicon is forming some V-shaped structure or enrichment along the V-shaped region, which is coinciding with this particular V-shaped defect. So this indicates that the 0.7% silicon added is going into these V-shaped defect sites where there is free volume. Now, if you really want to understand what are these V-shaped defects in 3 dimensions, we make the atom probe needle out of this material. That means we make this conical needle. Now you see the contrast variation within this needle in a 3-dimensional form, but there's a projected image in a microscope. You see the light region, which probably is responsible for higher amount of silicon present inside. You do the chemical mapping, then you suddenly see that in all of these regions where there is light color contrast, you see a significant amount of silicon enrichment. So it's no longer the V-shaped attraction, is more like a 3-dimensional nanoscale precipitate formation is what you see from a EDS map of a atom probe needle imaged using a transmission electron microscope. You take the same needle and then you look this in an atom probe tomography, then you are able to see that there are silicon distribution in a more inhomogeneous way, and there are nanoscale laminar microstructures visible in a 3-dimensional volume. But within the nanoscale microstructure, you have variations. That means there are some type of precipitate which are broader in width and longer, but there are some other type of precipitate which are narrower in width, but they are even extremely larger. Now that means even within these 2 nanoscale features, we want to understand the difference in terms of morphology, which we can do here. But now we are also interested in knowing what is the chemical difference between the two different silicon enrichments. We can do a concentration profile, and you can see here the first precipitate, what you see here is of a chromium 5 silicon 3 stoichiometry, whereas the second one is of a chromium 3 silicon stoichiometry. That means depending on the morphology, you have a chemical variation and possibly a structural variation based on the stoichiometric composition. So now one can realize that at the atomic scale, there are a lot more things that are happening, and even in the nanometer scale, you have a completely different chemical constitution of a phase, but they are distinctly visualized as 1 and 2 using this atom probe tomography, which was not possible by other methods as what you have seen before. So now if you want to understand why we are able to see something in atom probe and why we are not able to see something in other methods, that means the same material with 0.7% silicon, we looked at in TM, we are able to get a single phase diffraction pattern, but whereas if you look the same in an atom probe, we are able to see multiple types of silicon segregation in the form of a precipitate. If you try to understand this, from the EDS pattern, you can see these silicon distribution in the high resolution, whereas atom probe tells you there are two different types of precipitate exist, which is much more pronounced segregation compared to what you see in a TM EDS pattern. This means when you look this in a three-dimensional form, you see something. When you look this in a projected two-dimensional form, you don't see many things. And this is because these regions, what you see here, where there's a bright contrast, is responsible for disappearance of these kind of precipitates sitting on a grain boundary, which is a defect, because the sample preparation or the FIB-induced sample preparation can smear away all this information or by removing these precipitates preferentially from their ideal location. So these are called artifacts in microscopy, where some nanoscale feature disappears because of the preparation induced damage or because of the imaging induced loss or something that can happen during the imaging process. Therefore, some of these vital information on the microstructure and phase evolution can be missed out on these materials. Now, similar is an example in the bottom. As you see here, there are a lot of these nanoscale features visible in the microstructure on the same material. In the EDS mapping indicates there is no signal that is coming out of these nanoscale features, which means these are all holes in an ideal way. But if you look at the same in an atom probe, you can see all of these nicely arranged columnar features visible in this order, where it is all rich in this oxide content based aluminum chromium cobalt oxide. That means when you get this material in the three-dimensional analysis, you are able to get some information at the nanometer scale, which is not possible in a composite microstructure imaged in a projected geometry. So to avoid some of these loss in information, the new emerging technique of correlative microscopy has been evolved, and we are one of the groups in India doing this in an extensive way. That means now this is an electron microscope typical column. You have an electron column, you have a stage, and you have, for example, a diffraction detector. So you put a bulk sample, you can do surface imaging, or you can tilt it at 70 degrees so that the incoming electron beam gets diffracted based on the crystallographic nature of the material present inside. So you get a diffraction Kikuchi pattern. Now, once you get the Kikuchi pattern from a large enough area, if you want to get the nanoscale information, then you can identify which region of the bulk sample we want to get the information, prepare them accordingly in the form of a 100 nanometer thin sample, which is electron transparent, and everything happens in a scanning electron microscope. Then you introduce what is called a scanning transmission electron detector, which we have configured here. So this detector gets all the signals that are transmitted through this thin sample, which means the scanning electron microscope has now started behaving like a transmission electron microscope, and whichever beam, that part of the beam that gets diffracted because of the crystallographic nature of the species present in the thin layer. And now these diffraction patterns being captured here, and this forms the transmission Kikuchi diffraction pattern. And when you analyze these things, we'll be able to get transmission imaging in a projected geometry, diffraction information of the grain. So you get the orientation information, phase information, as well as the microstructure on the same geometry, and whatever X-rays that are being generated from the surface, you can capture in a EDS detector, so that you are also able to get what is the chemistry of those individual phases, all that happening in the same region of the sample at the same instant of imaging, so that all this information is captured at the same time. Now, this is an example that you have a macro scale component. This is a microstructure feature. You can enlarge and see in the microscope. You can do orientation imaging in a diffraction mode, identify the crystal structure distribution. Then if you want a finer scale information, you can produce in an electron transparent sample, do this nanoscale imaging as what I showed in the earlier slide, and the diffraction gives rise to the phase identification of different precipitates present inside. And if you want to know the chemistry of the precipitates at the atomic scale in 3D, then you take these things to an atom probe, and then you are able to see their atomic distribution in a three-dimensional form. So all of this can happen on the same location of your sample, so that every information that you get can be correlated one-to-one. So I'll give you a couple of examples of what we have done in this kind of a correlative microscopy method, which is the most emerging technique for nanoscale materials analysis. So this is an example of an additive manufactured material of a nickel aluminum bronze. We wanted to compare 3 different regions for their microstructural phase evolution. So this is an exact plot of one of these layers, which says it is a face-centered cubic structure, but we have some body-centered cubic structure precipitates sitting inside. Now, if you take this material in an electron transparent fashion, going to a transmission electron microscope, you can see here a defect, which is a grain boundary, which is separating the 2 grains, and you have these tiny little precipitates of nanometer scale across the entire volume. But to image something like this, we have to go to a large enough field of view and see a limited volume, but we don't know still about the orientation of these precipitates and their crystallographic nature. Even if you do a diffraction, we can do for only one of the precipitates. If you want to have a statistical information on these additive manufactured materials, which is crucial, then we cannot rely on a transmission electron microscope to get this information. So therefore, what we can do is that if you want to see nanoscale phases independently at the grain boundary, you can further zoom in, but you can see a dramatic reduction in field of view in the attempt of improving the resolution to look at the nanoscale features. So what we have done is a correlative microscopy approach, where we did the transmission Kikuchi diffraction on the same electron transparent sample. Now this grain boundary region is what you see somewhere here, and all these nanoscale precipitates, you can now get the diffraction information, identify for their crystallographic structure. That means all the blue color precipitates are body-centered cubic, and the matrix material is a face-centered cubic structure. So you can now see an entire large field of view of micrometer compared to the nanometer that you got in a TM can be mapped to for their crystallographic structure as well as the crystallographic phase. So this is an example of a Kikuchi pattern done across this entire volume. So millions of patterns are being obtained and identified for their structure as well as the orientation. So if you now want to know precise morphology of the precipitate and their chemical constitution, you can take these nanoscale precipitates to the atom probe, and you can see now only the iron atom shown here, but all the atoms are shown in the top. Iron atom forms 2 different morphology, tiny little nanometer scale particles, which are those little ones that you see here. And you know these are all body-centered cubic structure, and this is now giving us an iron-rich precipitate information. And there are bigger precipitates which are something like this, which are also iron-rich, but they are having a completely different morphology. That means you can now, for the same nanoscale feature, you can get the chemistry as well as crystallography by doing this correlative microscopy method. So this is another example of a same precipitate identified using a STEM image with a large enough field of view in the scanning electron microscope geometry, and you can do the diffraction, and then you can get the orientation information of the same precipitate what you see here with respect to their 111 or 101 direction, and then you can get also their crystallographic structure based mapping, where you can see whether this is a body-centered cubic structure precipitate or a face-centered cubic structure precipitate. So all of this information you can get from the same location. So this is a uniqueness about characterizing nanoscale features in order to understand their mechanical properties. So this is an example of atomic scale clustering, which you can scale it up and go to the atomic resolution and see these different features, and you can also get their chemistry precisely identified for this larger scale cluster. What is the iron aluminum concentration, because it's iron rich, also is aluminum rich, so you can get the precise chemistry, and therefore you'll be able to now understand what could be the property of this material when you have these kind of features inside. I show you a couple of examples before I end my talk. This is an example of characterizing defects in additive manufactured materials or even bulk materials. So this is a grain boundary between different grains, and there's a triple junction. If you are now interested to know what is a grain boundary segregation or precipitation that is happening on the boundary, you can specifically prepare this grain boundary alone. Look this sharp needle in the TM, and you can see the grain boundary is located here. So you selectively mill away unnecessary region, get this grain boundary at the apex of the tip, and do the diffraction so that you can see the body-centered cubic structure precipitate sits on top of the grain boundary, and the matrix is made of phase and cubic structure. You can get the orientation information. Take the same to the atom probe, then we will be able to see what is the precipitate phase that is sitting on a grain boundary. So different types of precipitates of BCC nature, which is chromium rich, which is B2 iron cobalt rich, all of these things sitting on the same three-dimensional volume can nicely identify with their crystallographic orientation, nicely identified with their crystallographic structure, and then as well as with their chemistry of these precipitates. Similarly, we can do it on any kind of a steel. So this is an atom probe needle on a grain boundary. The two color difference indicates that there is a grain boundary separating the two different orientation of the grain. You put this in an atom probe and you can see a carbon segregation on the steel sitting on a grain boundary, whereas there is no segregation much across the grain boundary. So all of these correlative things you can do these days to identify the nanoscale chemical distribution and the nanoscale phases present in a composite material. Okay, I think with that example, I hope I have convinced you that correlative microscopy enables you to study structure, chemistry, orientation, information, etc. at the nanometer scale. Finally, to conclude, we are at the forefront of developing what is called a field and microscopy. That means we are building this microscope from the scratch at IIT Madras, where we are now interested to have the atom probe needle being imaged for individual atoms also, so that we are able to see what is called a point defect, because until now all that I showed in grain boundary etc. are two-dimensional defects. But if you want to show almost a one-dimensional or an atomic scale defect, then you need this kind of an imaging where all these dots represent individual atom, and if an atom misses from its ideal crystallographic pole, then you know there are vacancies, Frenkel or a Schottky defect present inside, and this is the current state of the art that we are building at IIT Madras, and sooner by next year we should be having this microscope fully functional so that we are able to correlate the real atomic position in terms of crystallography as well as atomic position in terms of the chemistry coming from a nanoprobe. So we will be able to correlate both of these things simultaneously at the same time. So with that, I end my talk. I thank you for your attention. If you have any questions, I'll be glad to take over. Thank you.
Should I ask a question?
Yes, sir. Yes, sir. You can ask, sir. It's for Q&A.
Myself, Dr. Pankaj Kumar Singh from IIT BHU. Your presentation was very nice. My question is very simple. As regarding the atomic probe tomography that you have used, how it is different from the CT scan technology?
From CT scan. Okay. So CT scan in principle relies on secondary source. That if you want to image something, in a three-dimensional object, you need some source to enable this kind of an imaging. Whereas in an atom probe tomography, there is no secondary source being used. Your material behaves like a probe. That means your material is the source of imaging. We are only applying positive potential, triggering the kind of a field evaporation. That means individual atoms start from your material and these individual atoms are detected. Because of their atomic mass, we are able to identify which chemical species that is being detected. And because of the position of detection, we are able to know what is the 3D distribution. But whereas if you look at the any other form of CT tomography, right, it is a three-dimensional imaging, but it relies on a secondary source.
Okay, secondary source.
Compromise based on the wavelength of the source that you are using. Yeah, yes, sir.
Okay, you are saying right. Here in the CT scan, there is the use of the X-ray for the study. What
so
about
the
this
wavelength of your X-ray determines your
APT?
APT has no secondary source. No X-ray, no optical light, nothing. No. So we are only using the atoms present in our material to image the same atoms. No secondary source.
Okay, thank you.
Yeah, so there is no dependency on the wavelength issue. That means there is no restriction on the resolution controlled by the wavelength of secondary source that we are using.
Okay, thank you, sir.
Hello, good afternoon, sir.
Yeah.
It was a wonderful presentation, sir. So what I want to know is, with respect to color mapping, if you have the material in that scale, what it indicates, because I don't know what.
So like I said before,
for color mapping, sir.
Yeah. So the color mapping typically represents one chemical species. That means For example, you take a steel, you may have iron, carbon, manganese, all these together, right? Now, if you want to understand, even in the current slide, what you see here on the bottom left, the color mapping indicates different chemical species agglomerated at certain locations. That means knowing the color, you can know which chemical species is being agglomerated at specific location. Because the technique enables us to identify their precise chemical identity, and we can use this identity to map the three-dimensional space for their distribution. So all different colors represent different chemical species coming from the periodic table.
Oh, thank you. And
which is part of your material. Yeah.
with respect
Yeah.
to orientation,
Correct. Correct.
and we can come to know with the different orientations also, no, sir?
Yes, yes.
Thank you, sir. Thank you, sir.
We can do that. Yeah. Yeah. Thank you. Yeah. That's fine. Thank you. Yeah. 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 Mhm. Yeah. Thank you, Professor. Yeah. Thank you. Thank you. Yeah. Thank you. Bye.